Nie, nie.
Okay, it's my pleasure to welcome Michał Rams from IMPAN, and the title is Weighted Products of Digits in Continuous Fraction.
Thank you. Yes. This is what I will be speaking about today. It's a joint work by Okay, so what I will be speaking about, there is a line of research in the metric number theory about the general idea is that we have the continuous fraction, we have the Gauss matrix, which defines certain symbolic description on the 0-1 interval, on the irrational points on the 0-1 interval, and then we want to describe the how-to dimension of certain sets defined by some properties of the symbolic expansion. And let me maybe start by the paper by Wang and Yun. It was 2008. So they were looking at the set of points for which there exists a sequence of positions on which the symbolic expansion grows with prescribed exponentials. Okay, so that was kind of natural question. But then it turned out that, for reasons I'm not going to pretend to understand, it is interesting for the number theorists to also look at such sets of points where the product of consecutive positions, maybe in some powers, is growing at some exponential speed. The paper was
product seems related to Qn. So, the same speed.
well, AN is related to QN.
But
Product
Qn
is not really, there is very subtle difference between looking at one symbol growing exponential and the product of symbol growing exponential.
So here not Q but AN.
Yes, this is anyway, it means that somebody is growing exponentially fast with almost the same speed, but he can somehow distribute the things among them and optimize. I do not pretend to understand why it is important. Okay, but then people started to study things like this, so there was paper by yes, no, who it was that one. Wu and Xu that was looking at the set of points
somehow related with Bruno condition or
I know no relation.
So I should calculate some.
Because this is for some fixed b as the function of b. So each of those guys can grow exponentially fast, but slower than b. So this
So
is
it's B is
In
fixed.
average lower.
And M is fixed also.
And
no n.
M,
M is fixed. Yes.
M is fixed, so it is.
Okay, and then there was also a question.
and what did Kleinbock and Hausdorff do?
They were doing certain Bernstein inequalities. They were doing things in the number theory where it turned out that they need, and they did this for n equal 1.
Kleinbock was working some years ago with Margulis, so might be related to some dynamical systems. Geodesic.
They are usually doing this by the context methods, looking at the geodesic.
Yeah, that's what I remember. And these Chinese components from what city?
One who should have from Wuhan. One I don't remember. Okay, and you actually might have a little introduction about this topic now already, because Irina was giving a talk about it like half year ago, and she was talking about and they were doing the case when we have product of just two. Elements, but
What is T0 T1?
those are just some constant, positive constant.
Sorry?
Some positive constant.
There is it or there
No.
are fixed?
Yes, we fix B, we fix T0, T1. So, okay, I guess you can take everything to power 1 over T0, so you can think of T0 being equal to 1. But T1 is not going to be equal to 1, so this is kind of non-homogeneous situation when those digits are not equal. Okay, so as you may guess, what we are going to do is to look at the system
iteration of exponent.
So
So,
this is not
so
related
this is
to
much
Bruno.
slower growth than what appears in Bruno. It is something maybe diaphanous kind of condition.
Okay, so in order not to
No właśnie, to jest odwrotnie.
No, to not Johann. But I'm not sure. Okay,
this is about fast growing, it's exponential
Yes.
growth.
no, but it is not like iteration of exponent. Because Bruno says
For the
logarithm.
consecutive ends, the exponents are almost the same.
Uh-huh.
For consecutive ends, the exponents are almost the same.
No, it is not about exponents of a constant, but it is about the next is x of x of f of x something. That's p. Because it is logarithm of next digit compared with the previous. And they should be growing or not growing. It's about Bruno. And here we don't have x of x n times x, but we can just b in the power n. So this is something much lower condition.
I don't understand.
Okay.
Okay, so in order to not repeat the same proofs again and again for a slightly different system, a long time ago with LINGMI, we defined something that we called the decaying Gauss-like system. This is, well, it seems that people started to use it, so maybe it was useful definition. That is, it's the infinite iterative function system. With the following properties. Okay, first we are on the 0, 1 intervals and we have the maps mapping the whole interval into some subdivision of intervals. That is, the whole 0, 1 interval except the point 1 is in the image of the map. There are no gaps. The next thing is that, okay, for every epsilon there exists some c such that 1 over c I to power d minus d plus epsilon is smaller than f I prime everywhere, is smaller than c I to power minus epsilon. The c depends on the psi. Okay, that is the contraction coefficients decay like 1 over decay like I to power. Okay, this, am I missing something? Oh,
G bigger than 1.
sorry? G is plus larger than 1.
Larger than 1 plus epsilon.
Yes, there is one more assumption that, okay, then the system is contracting. Eventually contracting. That is, there exists some n.
Because the C makes it not contracted at the beginning. iterate, so standard Gauss is okay.
Yes, yes. For the Gauss map, for example, original Gauss map has derivative 1 at one
So
point,
second.
but the second iteration is already gone. So basically all the classical versions of Gauss map belong here. They are for d equal 2, of course. And okay, this is maybe useful tool, even though we haven't done some important work on this. And for this reason, people who worked on this were always assuming additionally bounded distortion property. Bounded distortion is something which holds for Gauss map, but is definitely not guaranteed by this assumption. This bounded distortion
For
is,
iterates.
sorry?
Bounded distortion for iterates.
Yes,
Yes.
it is that maximum of prime divided by the minimum this is smaller than some universal constant.
This
Oh.
is only interval to small interval or slightly extended,
This is on the interval of small.
so you are not interested in the extension.
No, I'm not interested in
Because
extension.
for different n maybe it extends a little bit, but it's less and less for higher. I could ask also about some C1 plus epsilon.
No, we are on
You
the
don't.
C1.
Okay, so. Yes, that's true. Maybe
We
it
are
doesn't
only
matter.
working with C1, and so the idea of extension doesn't somehow appear. C1 you can extend everything to everywhere.
No, but for iterates you have extension to smaller and smaller neighborhoods. For iterates.
C1 you can extend everything linearly on the arbitrary distances.
Okay, doesn't matter. Wystarczy.
Okay. So we are not going to assume bounded distortion. So one part of what we are going to do is to check finally what kind of distortion properties we have for that class of systems, and then to prove some basics of the thermodynamical formalism, that is in particular proof that we have pressure for the geometric potential if it exists, we will need it.
So you are not assuming bounded distortion property? No. Just what is of the
Just what is written here.
This was a long story. It kind of started like a talking about how to rewrite this theorem not for C1 plus epsilon but for C1.
Yes, but the big part of this theory is we need pressure. We need to know that pressure exists.
Yeah, and to assume only C1. I think how many years ago talking.
Okay, but for infinite systems, this was done by Mauldin and Urbański. But they had assumption that basically that the distortion in the first level cylinder is uniformly bounded. They gave some name to this assumption, I don't remember. But it's okay.
Because when you iterate, then the domain becomes decreasing. When the domain starts
Well,
decreasing,
domain
then this
is-
margin starts necessary margin also.
What was the name?
May make
They call it acceptability. And is some constant which bounds the distortion in the first level cylinders, uniform. And this kind of assumption, as you see, is not satisfied in our system. So we needed to make the proof of our own.
And now you're talking about your paper with Liao or your paper with
No, about this paper, yes.
with Irina.
Yes. In this paper of Liao, we're looking about the systems in which all the digits, about the sets for which all the digits were large. And in such situation, the distortion didn't play a role. And we actually didn't need pressure there also. Everything was much simpler. But here, when we are looking at the shrinking target type of systems, then here pressure will appear, and will appear the stretches where we have small digits, and then the distortion is going to be important.
So you assume some this was one of these conditions. Yes? What do you assume about?
We are looking at the sets of the
here.
form. And one paper I didn't mention exactly that kind of products on the dedicated Gauss-like maps was considered by Zhang, but he was looking at sets in which this growth was not exponential but polynomial. That is, he was describing this as being soup of logarithm of this divided by log n converges to something, and lim inf converges to something. So here we are doing the different option. So let's start by checking what kind of distortion we are going to have.
For original Gauss map, you do have this assumption of Mauldin and Urbański satisfied.
Yes, there is, for the original Gauss map, there is no distortion.
Okay. So, and you would like to try to continue, because you said that you need this extension for the paper with Irina, which was focused on Gauss map, or
No, this is our assumption.
Sorry?
This is our assumption.
This is a,
So the Gauss map is the special.
so you go beyond Gauss map.
Yes.
Okay.
So that we have Lurov's map and all those.
Lirov is the same.
No, it's not the same. It's not the same as Gauss map. Lurov is with linear.
Yes, but the same estimates for
Yes, so basically that's, well, there is no distortion.
There's no distortion.
No, I just wanted to comment that the C1 is of interest since long time.
Yes. I mean, when we can do something more, and we want to do something more.
Because you want to produce the tool of thermodynamic formalism in this setting, this general setting with no bounding distortion, but with this.
So this we hope that, well, might be also interesting for people, because why assume bounded distortion when you don't have to assume? Okay. So what are the distortion properties of this system? So it's not bounded distortion, of course. Another kind of distortion that appeared in the literature, it was tempered distortion.
What?
Tempered distortion. So exponential distortion, if you prefer. It is that the same thing is smaller than e to the power rho n with 1 over n not constant, but it is still sub-exponential. So as long as we do not look at the point with exponent 1, which we exclude here, this tempered distortion from the dimensional point of view is just as good as the bounded distortion. It's just as good as the bounded distortion, yeah? Because everything goes down exponentially fast. So if you are multiplying by something sub-exponential, it doesn't change a lot. However, this is also not satisfied in our case, obviously, because even for the first level cylinder, for n equal 1, our distortion is unbounded. So what we are making is something, we gave the name, we call it almost tempered distortion. Okay, so that is, we say that maximum of this derivative of the minimum this is to be smaller than okay, then for every epsilon there exists some sequence rho n epsilon such that 1 over n rho n epsilon converges to 0. This times
Okay, so now for n equal to 1, your assumption there is at least.
yes. That is somehow we put distortion as product of two things. One of them describes the small digits. When you have the small digits which are not strongly contracting, then however many of them we take, we are only seeing something sub-exponential. And the other part takes care of the large digits. And this thing doesn't depend on n, it is just about how large the contraction we have.
There is a notion second derivative divided by first derivative makes curvature, which is also this one.
Yes, we see one.
I see, but this ratio of this is somehow related with the second derivative.
No, we do not have any second derivative, so we cannot.
No, but I try to remember what does it mean non-linearity. Non-linearity by definition is second derivative divided by first derivative. So I'm thinking is it any relation?
Maybe yes, but
No, go on. Try to.
okay. And as you see, this kind of distortion should be good enough for Hausdorff-dimension estimation, because we have sub-exponential part, which doesn't change much, and we have the part which is basically telling us that okay, you take the size of the cylinder you have and you take it to power 1 plus minus epsilon for arbitrary small epsilon. And this is also not going to change the dimension by more than epsilon. But you can take arbitrary small. So that kind of distortion should be enough to do, and it will be enough to to do all kinds of dimensional work that we want to do. Okay, so to prove this thing, well,
So prove that this holds under your
yes,
assumption.
yes.
Mhm.
The proof is basically trivial. This we write the chain formula, so this thing is not larger than the product of times maximum of I2 prime, but restricted to the F1 interval over minimum and so on. And then we can break this product into two parts. We take some I large enough that this I to power t, I to power epsilon starts to be large. Then we take the product over all the smaller guys and we estimate it in the usual way by the some exponential, because we know that those sizes are going to 0. We don't care how fast they are going to 0, they are going to 0, and this means that the modulus of continuity of the logarithm of the derivative is going to 0. And when we have the sequence going to 0, then the sequence of averages of this sequence is also converted to 0, and this is basically the end. And we have the reminder that is the big guys, but over the big guys we have just this epsilon bar.
This this non-linear dimension is just a two-dimensional derivative of local derivative of
Yes. This the
Another
variation of
expression.
the logarithm derivative.
another expression of non-linear.
Okay, so indeed we have the formula like that. Okay, so how do we prove that we have a pressure? That is what
How do we prove what?
we now want to prove that we have pressure for the geometric potential. That is, let me look at the notation. Okay, denote Zn of S, let it be the sum.
Wielka suma statystyczna.
That is sum over I1 IN of diameter of the C I1 IN over C I1 IN is the cylinder described by the symbolic sequence I1. Okay, and we want to prove, okay, we write Pn of S is 1 over n logarithm of n of S, and P of S, we want to define as limit and then what we need. And why does this limit exist? So let's, and normally we try to somehow prove submultiplicativity and use some version of a catalan. So what we can say here length n over the alphabet of natural numbers. Okay, so this is okay, and now let's write what it is using the distortion. So this is smaller or equal. Okay, we would e to power k rho n epsilon times times sum over omega 1 omega 1 power s 1 minus epsilon times sum over omega k omega power s 1 minus epsilon. And we have also similar bound from the other side. We have e to the power minus k rho n epsilon, and here everywhere we have the power s 1 plus epsilon. Okay, so in other words, we can say that s is more or equal than e to the power k rho n epsilon Zn of s 1 minus epsilon power k and greater or equal than so this is almost what we want, because if we fix some small epsilon, then this thing, when we go with k to infinity, it is not going to be any important. And basically what we have is, when we take the limit of kn going to infinity and we divide this by kn, then we will have something like 1 over n, sorry, Zn of s1 minus epsilon to the power 1 over n minus this, and this is, well, this is basically Pn of s1 plus epsilon minus Pn of s1 minus epsilon. Sorry, that way wrong. Pn of s1 minus epsilon minus Pn of s1 plus epsilon. And this is the maximal difference between lim sub and lim int, and if we go with epsilon to 0, then we would want to say that it goes to 0. But the problem is that we do not really control n. That is, when we take some small epsilon, then we need to take some large n, so that this rho n epsilon is not important. So it's not that for some fixed n we are looking at the difference between values of Pn at some close places, but we have to have some kind of uniform bounds on how much those Pn's can vary. If we have some kind of uniform continuity bounds on the work on Pn for every n, then we are done with all the existential version.
Minkowski.
Minkowski.
The second derivative is clearly positive object. Okay, and what do we know from this? And some other thing is we have some bound. That's for we have some bound. For every s larger than 1 over d, we have some uniform lower bound and uniform upper bound, such that every function Pn is between them. How do we get this bound? Well, okay, I erased that definition, but we have the lower and upper bound for the derivative everywhere, and we can just write the pressure for this minimum of derivative or for the maximum derivative. And this will be the bound for pressure for every n. If we see, this will be bound for P1, and this means this will be bound for every n. Okay, but what we have then is that if we have convex function between two functions, then we automatically have the bound. That is, let's write here point A, here point B. We know that our convex function Pn, let's call this, let this be G minus, and let this be G plus. So Pn of B is greater or equal than G minus of and Pn is smaller or equal than G plus of n. And this means that there exists some point S in the interval AB such that Pn prime of S is greater than G minus of B minus G plus of A over B minus A. Greater because this one is negative. And at the same, and if this is so, then it implies that for every t larger than S, we also have P and prime of t greater than G minus of B minus. That's okay, over B minus. And of course, this is everywhere smaller than 0, this, those pressures. Anyway, a similar way you could get the upper bound, but you don't need to do upper bound because those functions are fixed.
Okay, so what was the final?
So the final thing is that all the functions Pn have uniformly bounded derivative.
I'm using these two only, the lower and upper.
Yes.
Okay.
Just lower bound, upper bound convexity gives the uniform
The
bounded
AB
derivative.
play no special role.
And n is not important at all, so this is uniform bound working for every n.
Fine. Nice.
Okay, so this ends the proof. So this ends the proof of the existence of pressure. Because the only thing that we needed to make this work was that to know that Pn of S1 minus epsilon minus Pn of S1 plus epsilon uniformly goes to 0 with epsilon going to 0 independently of n. And this is what we proved. Okay. How much time do I have? the large digits don't make impression on the pressure. There is again some tiny trick to do here, but basically it's not complicated. Okay. So we have the theoretical basis, so we can at least formulate the theorem. So let S be the syntax. Where those TIs are those exponents in the set that is still visible here that we want to okay. Then for M equal 1 to K, we put out AM BS equals T minus 1 times SPM plus TS minus 1 sum from 1 to M minus 1 J A of PS let be the maximum over M S and A over S is the minimum over V in the simplex S, very beautiful. And the theorem says that the Hausdorff dimension we are calling E is equal to infinity of S minus Q of S smaller or equal to A of S.
Because this E is defined in terms of original Gauss map. Now then we move to more.
No, this definition works for any infinite.
Okay, I want like.
That's just a condition of the coordinates.
Okay, so that we have infinite collection of maps Fi which satisfy this, and they are somehow labeled.
Yes, they are labeled in the order.
In the order. Okay. So in this, but are not as good as Gauss maps, so we have to play with new. First proving that the pressure exists, and now.
Yes, so in particular, when you substitute D equal to 2, then this will be the result of the Gauss map.
So
if you substitute D equal to 2,
and
then
D, where is D? D decaying, but.
Yes, that's the derivative shrinks
okay,
like I to power minus
okay,
D.
so it's 1 over I squared for Gauss map. Okay.
Okay, so this is the.
But for Gauss map itself, it's also new.
Yes. You know, it is new for the Gauss map. We just decided to write it in a bit more general ways, not to.
No, it's
Usually one writes this where P(s) less equals 0. So this expression pretends to be 0 in standard situation.
Yes, but P of S is the pressure for the full map, so it
No,
has to separate
I'm
something.
just reminding standard
The
for
this-
iterated function system.
No, thanks. We are talking here about the shrinking target set. And for the shrinking target set,
so it is
the
different.
formula is not the pressure equals 0.
No.
It's exactly of that form if the pressure is somehow related to the target.
Well, maybe 0, but you
To modify the
you
pressure.
adjust other definitions.
What is K here?
K is the number of. I'm sorry. Okay.
Okay.
Should be clear.
This.
And in the formula there is no dependence on the choice of i's. Only
Yes, I am totally irrelevant. They were just actually added for fun because they are not going to impact anything. Okay, so there is the beautiful formula and
This is now I understand that it's a shrinking target because with growing n conditions change. The target
yes,
is
and the
shrinking.
condition is to be satisfied only at infinitely many places.
Standard situation of the dimension is as if we use the Hausdorff for z square on the set.
What is capital E?
It's just some constant that we.
That.
Well, here it is infinite iterated function system, so it is
Okay, so I'm sure that you see what is the meaning of this formula.
Oh yes, it's transparent.
unbelievable.
You should know it. It's not difficult. Okay, so
Natomiast B minus 1 coś to.
That is
so how does one work with the integrated function system? Because if you are used to the finite integrated function system, then you always look at cylinders and you try to cover your set with cylinders and say that this is going to be a platform. Situation is different for the integrated function system because you need to consider another type of intervals. Okay, so you have the cylinder. Okay, this is some plural.
The size here, it would be just the product of AI to power minus product from 1 to n. Okay, this would be also product from 1 to n minus 1 AI to minus 1 times a n plus 1 power minus b.
Okay, so what we get when we sum those things up?
Well, the length of this would be product from 1 to n minus 1 AI to power minus b times a n to power minus b plus 1.
Because we are taking here the sum of
The length of the
n to power minus d from some n to infinity. And this sum is approximately n to power minus b plus 1. That's a constant sum.
No, giga. The giga order up to
Okay, so that kind of object we are using to cover the sets in the infinity graded function systems of the Gauss type, and they are going to produce the optimal. Okay, and when we look at this, then we see what we have here. It's exactly the same. Okay, so let's have some use of this. So let's make that upper bound. So okay, I'll erase, but we can assume that for some n we have
A n plus I1 to power Q1 times a n plus This is simply rewriting this thing.
This size larger than 1, and then we.
Then it means that you can decrease the last element so that the sum is equal to 1, and then we put 0 on the following coordinates, and this is a point in the surface.
So it's larger than 1, so how do you make it smaller than 1?
By decreasing the last element.
That's why this is some c which is smaller than.
Perhaps negative.
No. This we assume that m is the smallest number for which this sum is greater or equal than 1.
Okay. So it jumps above, but not much.
It just jumps above at this particular place. Before it was still smaller than 1, and so we decrease, but we decrease to something which is still positive.
Mm-hmm.
Okay, and this means that x belongs to this set D on the sequence
What is
block.
x?
Well, x is the point. This x is the point at which those things happen.
Mm-hmm.
So x must belong to D of, okay, first we have some arbitrary digits on the positions before n plus I1. We don't know anything about those positions.
Mm-hmm.
Then we have this A n plus I1. Okay, then we have again some relevant A n plus I2.
Mm-hmm.
A n plus I n minus 1, and then we have this C.
Mm-hmm.
Because all those things are exactly the coordinates of x, and this coordinate at the position n plus im of x is greater or equal than c, which means that x belongs to this union.
Mm-hmm.
Okay, so this is what we are going to use as the code. And what do we get from this? So what is the sum of the diameter of this set to power s? Well, first, we have this initial set. Well, I'm at the moment ignoring the distortion. But as you can imagine, the distortion is not going to change this calculation significantly. That is, it can change by some epsilon, but we can make this epsilon very small. So let's forget about distortion. Let's just write the main part of the object. So first, we have to take the sum over all the possible choices of this initial n plus I1 minus 1 symbols. Okay, so this will be simply the sum over all possible words of length n plus I1 minus 1. It is basically n. So it will be something like e to power p e to power np of s.
Where P is negative.
P is positive.
Okay.
multiplying by something like that. Okay, what about those positions? They are irrelevant. They are irrelevant, that is, we would have something like e to power I2 minus I1 plus minus 1 e of s times e to power im minus I m minus 1 minus 1 e of s, but all those things in the exponent are just constant, and so we can ignore them totally. What's important is what we see here. I mean, what those x. Okay, so it will be times what? Times product from 1 to n minus 1 a n plus I j to power minus ds times a n plus I m to power minus minus 1. Okay? And what? And then but there is one important thing. There is one important thing is that here we have to take also the sum, because those ANs, it's not one possible AN. There is some whole collection of possible ANs. It will be the sum over all. This will be the sum over all B belonging to S, such that AM is the dominant one. That is, this A of BS is the maximum over M. Okay, and what in particular would matter in this sum? Well, basically, how to explain it? We are basically divide. That's what we are looking at. 1 over n log b. N plus I and we want this, we divide this into the blocks, we divide it into the blocks of psi sub psi. Okay, so what does it mean? It means that A n plus I j is between b to power n k and b to power n k plus epsilon.
But this k is in the relation with.
Sorry. L. Okay, and P of S times sum over L of B to power n L times B to power n L1 times A and this B to power L times B to power minus D as L1. And this is this.
Yes, so the sum of over L, and now L1 appears, and now
Sum over L1 L n minus 1.
No, L minus 1.
N minus 1.
Mhm.
Okay. Times B and L2 B to power minus D as L2 times B and L n minus 1 B to power minus D as n minus 1 up to n times times the last thing that is this, and in this thing we do not have unions. We do not have many A's because all those different A's are in the same D set. Because this D set is the union of everybody. So we're not repeating this D set many times. So here we have only B to power minus D minus 1. Okay. And when you look at this times this, and you want this to be equal to 0, that is equal to 1, that is the exponent to be equal to 0, then you are now seeing exactly this formula. This is this exponent that you see here, and you see exactly this formula, that is this part which is positive, must be smaller than the negative part that we get from here, which is this.
At some point you started with choosing, so having X satisfying this, you choose N for which this happens for the first
Yes.
time. So
Yes,
now to
yes,
have to
yes,
use it.
and then okay, then we this is the cover for those x's for which this happens at time m, and then we have to take the union over all things and okay, I don't know how to explain it in the
Okay, but there is another step to
yes, there is
the problem.
this is a description of part of the set. Every point, for every point there exists some right m, and every point of the right m is in this covered by this cover at time m, and then because a is the maximum over m of this am, so actually the best cover is still one of those. So I mean, the best cover is the union of those covers, but the exponent of the best cover is still given by the formula. Okay. I guess I'm not going to do much about the lower bound. I will just tell you what we are doing. And then maybe wave my hands a little bit. Okay, so what do we do for the lower bound? Well, basically, first we are looking at this formula and we are taking this b for which this minimum is achieved. This is the only b that we are going to play with. And then what we do is we are taking some very fast increasing sequence mi, that we want. Okay, what do we do on every other position? What we want I smaller or equal than some capital M for I smaller, well, strictly smaller than M1 plus I1, and also for I smaller than ML plus I1 but larger than ML minus 1 plus IK. And all those areas between before the first target and between the targets, we just want the AIs to be uniformly bounded. They are going to be uniformly bounded by some number M, and this number M is such that the pressure for this restricted system to first M symbols is already close to the full pressure. Okay, what we are left? Well, we are left those I's those I's between IL and for I which is smaller than ML plus IJ and larger than ML plus IJ minus 1. Here, those are irrelevant parts, we simply put 1. Or 52, it doesn't matter what we put there. Okay? So this thing is full description of the set on which we want to look at. And it's clear that this set is contained in the shrinking targets. We don't need to get the lower bound for this set. And what we need to do, well, we distribute some measures, but quite clear how we are distributing it. Because here, at least here we are uniform distributed. Okay, but what we are doing here? There is one more technical tool that we did that I haven't told you about. And it is as follows. That for every finite M, we are taking the system restricted to the first M symbols, and for every S, there exists some measure mu S such that for every n and for every word of length n, mu S of C omega, it is, okay, smaller or equal than the diameter of C omega to power S times e to power certain rho n, and greater or equal to the diameter for minus rho n. Look, those rho n e to power rho n sub-exponential. What this measure is? What is the usual conformal measure? Okay, and this is the measure that we put here, and this is the measure that we put on each of those blocks. Okay, and now when we are trying to calculate local dimension of this measure, what we see Okay, what S is going, for which S we are going to distribute this method? For this S, which we suppose is the Hausdorff dimension that we are trying to calculate. Okay, so here, okay. I don't know, at least it's somewhat larger than this. Then we have those positions. And 1 plus I1, and 1 plus I2, and 1 plus I2. At those positions, we have this very bad restriction of the sequence, because we suddenly demand that the point is very large. So what is the local dimension there? Again, it turns out that the local dimension, you should not calculate actually the size of cylinder, but at the size of ball, of this D set. Okay, so this is something like this. This is not for the cylinder, but we are dropping, but we are not dropping below this. Then those intermediate parts are not important. All the time here we have the lower bound, which is like S minus epsilon, something like this. And this comes from the similar kind of estimation of what is the measure of this order. Okay, and then what do we have? Then we have the long time between N1 and N2 when we are again putting this as measure. So this again grows. And then we are again some drop of dimension around N2 and so on and so forth. We needed to calculate what is this local dimension of every scale going to 0, and well, we were able to prove that the inf of the local dimension is indeed greater or equal than S minus something depending on epsilon, minus something depending on M, on this choice of digits, and minus something depending on what those Ni's are. And all those three negative things can be estimated, can be bounded as arbitrary small. And this is
Okay, thank you very much. Are there any questions? Maybe online? So maybe you can something, I don't know if you want, but maybe you can now say a little bit about why about number theory.
I'm afraid I'm not going to be able to answer this question.
Okay.
I can give the reference. Kleinbock and Wadleigh. Just calculating dimensions, which is the person.
All right, so no more questions, let's say. And this, I guess, is our last seminar for this year.
No meeting with coffee.
Yes, so we had planned to make a social meeting, but because of some reasons we decided to postpone it to next year.